Hello friends, once again and welcome to our very journey of set theory. Well, without forgetting the very great contribution of Sir George Cantor, let us quickly recapitulate what all we did up till now in our last two lectures. The starting we did was from the very motivation of how the layman word sets entered into the world of mathematics. After that, I shared with you the experiences and the struggles which all the mathematicians had, after which Sir George Cantor came to their very rescue and successfully established the very definition of sets, which was that a set is a well-defined collection of objects. After this, we had understood the crux, the very significance of the word well-defined, and that was portrayed to you with the help of certain real-life examples to which you could certainly associate. And once we were completed with that, the very feeling of getting and understanding what a set is, it was now turn to deal with those sets which are frequently occurring in our journey of mathematics. Well, they were the collection of natural numbers, collection of rationals, positive rationals, reals, positive reals, integers, positive integers, and the massive collection of complex numbers. Okay, we had reserved symbols for each of these sets because this was done to make the convenience usage of these sets because they were occurring again and again. Well, this particular idea was very successful and I had told you to remember the symbols. I hope you have remembered them and they are at the tip of your fingers. Once we were completed dealing with those sets, it was now turn to understand how to visualize sets. Because unless you learn how to visualize sets, it is very difficult to deal with them in your papers or in your real life. And that is when I told you that there are two primary ways to represent or describe a set. A very elaborative form of description of a set, also known as extensional form of description of a set, was the roster or the tabular form, in which you were supposed to collect the elements which were sitting in the set, make them or place them in the set, separate them with the help of commas, and a starting brace and an ending brace. After that, the very second method of describing a set, which was my personal favorite, was the intuitiveness of describing a set. It was known as the intuitional or instinctive way of describing a set, and the name was set builder form. What do we do over here? Over here we have a characterizing property or a rule which governs all those elements which would be sitting in the set. Well, over here the members or the objects, whoever satisfy this rule or have this particular property inside them, qualify to be members of our set. And this is how our set is formed in the set builder form. We had dealt with certain examples of roster and set builder form, and I had ended my lecture at a certain question. I hope you guys must have completed that question and done it successfully with flying colors. But let me take you to the very same question so that you can tally your answer with mine. The question was, we were supposed to describe the set in the roster form. The set was that the set of all letters in the word mathematics. Now, once you know that you have to collect the letters in the word mathematics and also that the description has to be in roster form, what was the technique that was told to you in order to write a set in the roster form? For that, the very first task was to start your brace and end your brace. But in order to fill in the members inside this set, it is very important to understand what the members are. And once you will come to know the members, you just have to pick them, place them and separate them with the help of commas. So let us try and find out what all letters in the word mathematics are actually used to complete this word. If we look at this carefully, the word M is used as a letter in the word mathematics. The word A is used as the letter in the word mathematics. T, H, E, again M. But I am not supposed to write M again because it is not distinct. And last time in the last lecture, I had told you a refined definition of sets which we had concluded. And it was that a set is a well-defined collection of distinct objects. While studying the roster form, two important points of notes we had written, and one of them was that repetition of the members do not affect the nature of the set. And that is why while making the set, I am not going to consider M twice in my set. So the distinct members are M, A, T, H, E, not M, not A, not T, but I, C and S. These are the distinct members or the distinct letters of English alphabet which combine to make this word mathematics. Once you know what all members qualify to sit in the set, just put them in the set. M, A, T, H, E, I, C and S, and separate them with the help of commas. Well, this is it. This is our roster form of the set which is of all letters in the word mathematics. Let us move on to our next query, which basically gives us a task to write the set or express the set in set builder form. The question is, describe the set in set builder form. What is my set that I am able to describe or asked to describe in the set builder form? My set is A. Now look at this very interesting set, okay? It is 1 by 2, 2 by 3, 3 by 4, 4 by 5, 5 by 6, 6 by 7, 7 by 8, 8 by 9 and 9 by 10. These are the members sitting inside set A. Mind it, if you carefully observe, this set is actually given in the roster or tabular or elaborative form. I am asked to find a rule which actually all these members in the set are satisfying, because only then will they qualify to be inside set A. In order to find the rule or a characterizing property which is shared by all these members, it is very important to observe them and find what is common in them. Now, if you observe here carefully, look at the numerator. If it's 1, the denominator is 1 more than the numerator. Over here also 2 and the denominator is 2 plus 1. 3 and the denominator is 3 plus 1. This is the pattern being followed by every element, every member in this set. The numerator is a natural number and the denominator is plus 1 of the numerator. So alternatively, I can write my set A as 1 upon 1 plus 1, 2 upon 2 plus 1, 3 upon 3 plus 1, 4 upon 4 plus 1, and so on till 9 upon 9 plus 1. This is how I can express my set, but only when you have observed the behavior of every element lying inside A. Now, if you observe again, this one is common, which is being added to each and every denominator. This one is not changing. What is changing is the numerator 1, the numerator 2, numerator 3, numerator 4 and numerator 9. Why am I only marking the numerator? Because whatever you put at the numerator, that is what is coming as a term here. Whatever you put 2, then 2 is coming here. You put 3, 3 is coming here, 4, 4 here, and 9, 9 here. That means I am only and only supposed to vary the numerator, and that too from 1 to 9. I am not covering all the natural numbers. I am just covering natural numbers from 1 to 9. And therefore, my rule is super ready to be written. The rule is, in this set there are members of the form n upon n plus 1, where n is varying from 1 to 9 and my n belongs to the collection of natural numbers. This is the very set builder form of my set, because it gives you the rule which is governing the very formation of the set. Whichever elements satisfy this rule, that they are looking like n upon n plus 1, for any n between 1 and 9, they will qualify to be inside this set and become members of it. This was a question basically to teach you how to work on the rule to make a set into its set builder form. Once we are thorough with the technique to converting sets in roster and set builder, it's now time to enter into the diversified world of sets. Well, the mathematicians, when they entered into the theory of sets, basically Sir George Cantor's contribution, big contribution, in that scenario, while dealing with all the sets, they discovered that sets are having certain properties, inherent properties of their own. And that is when the classification of sets actually happened. And this particular idea of classifying sets into distinct varieties was brought and theory was presented upon it. This is very next topic that we are going to study in detail. Basically, once you have made a command over different varieties and types of sets, trust me, in your paper, you are going to outshine everybody else because you will have an edge over every other student. So let's get started with this very interesting topic of types of sets. In order to study the very first type, let me bring before you two very nice sets. Suppose I give you a set A, which is all those x belonging to the collection of real numbers such that its square is equal to -2. And if I am giving you my set B to be equal to all those x which are members of natural numbers such that those numbers are lying between 4 and 5. It's now time to actually deal with the fact that which members are lying in these two sets. Let us observe the very first set. Can you give me the members of this set? Well, let's try and work that out together. This particular set is asking for such real numbers whose square is -2. Well, if any real number is considered, once you square it, it becomes non-negative. Square of any real number is non-negative, by which I mean that it can be either 0 or it is strictly positive. But over here, this set A is asking for such x whose square is negative. -2 is less than 0. Well, this is absurdly wrong. This means there is no real number whose square is -2. But set A is actually a set, so it will have a starting brace and it will have an ending brace. What is sitting inside this set should be a member satisfying this rule. But there is no member satisfying this rule, which means there is nothing sitting inside this set. This set contains nothing because there is no member satisfying this particular rule. Let's try and observe set B. The elements which would lie in set B are those natural numbers which are strictly greater than 4 and strictly less than 5. In order to understand these members, let us quickly draw a number line. The number line is this. I am not extending it. You know that the numbers to the right of 5 keep increasing and numbers to the left of 0 keep decreasing. I am asked to find natural numbers between 4 and 5. So I have to collect those natural numbers which are strictly greater than 4. On the number line, strictly greater than 4 means strictly to the right of 4, which means I have to move to the right of 4. X being strictly less than 5 means that I have to actually travel to the left of 5. So I have to move to the left of 5. What is the common portion? Basically, the common portion will be those members which are greater than 4 also and less than 5 also. I am not interested in members. I am interested in members which are natural numbers. Can you see any natural number which is strictly greater than 4 and strictly less than 5? Can you see? Because I can't. There is no natural number between 4 and 5. After 4, the very first natural number which comes is 5. And before 5, the very first natural number which comes is 4. And therefore, there is no natural number which is lying strictly between 4 and 5. So what does this set turn out to be? This set also turns out to be a set having nothing. This is what is the very first category of sets which were discovered by the mathematicians. Because these sets had nothing inside them, in English or in layman language, I can say that these sets actually are empty. And this was it. The name given to such sets was empty sets. It was a wonder that how somebody can actually discover such sets, because the very definition of sets was that it is a well-defined collection of objects. But here, there is no object inside the set, still it is being called a set. So this was pretty natural but uncommon to the discovery of mathematics. Let me give you a very brief idea of how these sets work. Suppose I give you a collection C, which is all books having sensory organs. Well, by this I mean that I am searching for a certain kind of a book which has ears and it has eyes, it has a nose. Do books like these actually exist? Well, do books have sensory organs? This kind of a scenario is absolutely wrong because there does not exist any book which has sensory organs, and therefore set C is also equal to empty set. This particular set C was actually presented before you to make you understand that you can play with empty sets to the extent you want to. You can create empty sets at the tip of your fingers, at the tip of your hat. And this is when you will actually get the feel of how empty sets work. You can play with them and spend a lot of time with them because they are very, very realistic concepts. In order to get to the formal description of what empty sets actually are, this is very important that you note all these facts down in your notebooks, because then I will be moving on to a formal discussion on empty sets. So guys, are we now ready to actually understand what is the very formal structure of empty sets? Let me quickly give you a brief idea of what new you are going to discover. In these examples, we had the notation of a set having nothing inside it. But is this the only way of representing empty sets? Well, you have to wait for that, because I have a very, very new mathematical symbol to offer you which is going to replace these empty braces. And now we start with our very formal description on empty sets. Any set A is called an empty set if it does not contain any members inside it. Or there is one more mathematical way to write, which is x belonging to A is not true for any x. This is what I like the most about mathematics. It has its own way of expressing itself. There is a language of mathematics which it has, and this is what is here before you. What does this statement mean? It says that x belongs to A is not true for any x. By this particular line, I mean that x does not belong to A for any x. Wasn't this smart? Because the very fact that an empty set contains no members is same as x does not belongs to A for any x. You should be thorough with the mathematical language if you are aspiring to become an upcoming mathematician. I had promised you to give you a particular mathematical symbol, and now it's your turn to wait for that symbol, but the wait is over because the notation which is used for empty sets is equal to, well, what is it? You just have to make a circle or an oval and strike that off with a vertical line. This particular symbol has a name. It is called PHI, phi, whereas many people call it phi also, and this particular symbol, this notation stands for the empty set. You can write this or you can write vacant brackets. It is one in the same thing. But generally in your papers, in your books, in your reference sample papers, you are going to find this particular symbol written. Now that you are studying mathematics, you should be thorough with what the notation of an empty set is in mathematics. Okay? Let me tell you that once these empty sets were studied, there were two more special names given to empty sets. These names were empty sets are also called null set or void set. The fact that these sets are empty gives them a synonymous names which are null and void. Both null and void basically in English language mean empty only. And so whenever in your papers or in your books, if you find rather than empty, you find null set or void set written, don't panic, because it is the same as the empty set. Okay? Now it is the turn to unfold the very mystery of what the second category of sets are. Before that, let us try and work some sets out. If I give you a set A which is equal to all those x belonging to natural numbers such that x square is equal to 9. And on the other hand, I give you another set B which is all those x again belonging to natural numbers such that x is strictly greater than 4 and strictly less than 6. In order to unfold what these sets actually are, it is important to find out which members belong to these two sets. And for that, it is important to understand which natural numbers on squaring give you 9. What are the natural numbers which on squaring give you 9? Well, if I sit back, relax and recall, number 3 on squaring gives me 9. Number -3 on squaring again gives me 9. So yes, I have two numbers 3 and -3 which on squaring give me 9, and there are no other such numbers. So am I going to include both 3 and -3 inside set A? No, that's a word of caution for you, because the very fact that you only have to put natural numbers inside this set makes you eradicate the very presence of -3 in set A. And therefore, set A will only have one element, which is 3. If we try and understand set B, I am asked to collect those natural numbers which are strictly greater than 4 and strictly less than 6. In order to do questions like these, it is important, advisable to draw a number line. Now, if I draw a number line, then now it's very easy to observe which natural numbers lie between 4 and 6. I have to move to the right of 4 because I am asked to collect natural numbers which are greater than 4, and I have to move to the left of 6 because I have to collect natural numbers which are less than 6. Can you see any natural number between 4 and 6? Yes, I can, and definitely you can too, which is the very number 5. Is there any other natural number between 4 and 6? No, there isn't any natural number between 4 and 6 except 5, and therefore this particular set turns out to be a set having only 5 as its member. Why did I present examples like these before you? If you carefully observe, the very first set we did was empty set, a set which had nothing inside it. What is the next natural case that should have happened? It was that one element belongs to the set. This particular category of sets where just one element belongs to the set was the very second category of sets studied by mathematicians. And these are the class of examples from that particular category of sets itself. They were the very special Singleton sets. The name of these sets was Singleton only because these sets contain a single element. Okay? Now it's the time to start a formal description about Singleton sets and make you actually learn what these Singleton sets are. So what is a Singleton set? Yes, we have visually looked at them, felt them, read them and dealt with them, but we have not formally described them. Let us now formally describe the Singleton set. Any set A is said to be Singleton set if it contains only one element, only one or a single element inside it. This is what is a formal description of what Singleton sets are. You would be wondering that I gave a symbol to the empty sets, which was the symbol phi. Is there any symbol reserved for Singleton sets too? Well, yes, there is. The notation which we are supposed to use in the case of witnessing any Singleton set is Singleton A. Whichever A which belongs to the particular set comes out as the only element sitting inside the set. By looking at the very picture of this symbol, you have to declare that it is a Singleton set. In a similar way, if I go back to my empty set definition, the moment you look at the symbol phi, you have to declare that this is an empty set. Okay? That is why these symbols are formed to make our work easy. So that just by looking at the symbols, the very nature of the set is in our minds and we are ready to work with them. In a similar way that I had made a playful application of empty sets, you can very nicely develop some playful applications of Singleton sets too, and that will make you realize how much they are applicable in real life. We are going to move on to our next category of sets waiting for us, but only when you have these in your notes. So guys, till now we have made an entry into the world of two types of sets. The first one was empty set and the second one was Singleton set. From the set having nothing, we moved to set having just one element. And therefore, Singleton sets are never empty sets because they have something sitting inside them. Now, in order to give you an intuitive idea about the next very category, let me bring you to the world of three interesting sets. The very first set, set A, represents the four suits of playing cards: the spades, the hearts, the diamonds and the clubs. Similarly, there is set B containing -5, -7 and -9 as members, and I have another set C containing the first 5 alphabets of the English language. Let us do an exercise. Pick up a pen or a pencil, and in my case I have my chalks, and start labeling the members of every set with the help of natural numbers. What do I mean when I say this is that take the very first position which is sitting is the spade. The second is the hearts, third is the diamonds, fourth is the clubs. This is it. The very position will give you the natural number which will get assigned to these members. The first member gets the natural number 1. The second member gets the natural number 2. The third member gets the natural number 3. And the fourth member gets the natural number 4. Similarly, try and label the members of set B with the help of natural numbers. So how will you start the labeling? Well, -5 sitting at the first position gets labeled as the natural number 1. -7 gets 2 and -9 gets 3. Moving on to set C, we have A getting assigned natural number 1, B gets assigned natural number 2, C gets assigned natural number 3, D gets assigned natural number 4 and E gets assigned the obvious natural number 5. Why did I make you do this? Basically, these three are examples of sets wherein we were able to label the members or list the members by natural numbers. And over here, while labeling, if you had observed, this labeling process stopped at a natural number for every set. For set A, I started labeling the members and the labeling process stopped at 4. In set B, I started labeling the members and the labeling process stopped at the number 3. In set C, I had started labeling the members, but this process of labeling stopped at natural number 5. This stopping of listing, stopping of labeling the members of sets with the help of natural numbers is a quality not every set has. The sets which have this particular quality are known as finite sets. In a finite sets, they have this beautiful property of making their members list with the help of natural numbers firstly, and secondly, this listing process stops at a natural number. For set A, for set B, for set C, we have witnessed that. And so, this is what constitutes to be the class of the very third category of sets, which is the finite sets. Before I move on to a formal discussion of finite sets, let me present before you a certain question. The question is the empty set, which is denoted by phi, is a finite set? This is what is the question. The question is asking that A, B and C, they were not empty sets because they had something inside them at least. But is this empty set a finite set or not? Well, the very rule or the very technique, the very idea to decide whether a set is finite or not, it should be possible to list or label the members of the set by natural numbers, and along with a very important thing, that this labeling process should terminate. It should stop at a natural number. Well, to do that with the empty set, let us start with the solution. Suppose my set A is my empty set, which is also given by vacant brackets or empty brackets. In order to declare if it is a finite set, I will have to label the members of this set with the help of natural numbers. In order to label the members, there should be some member inside this. But there is no member inside this, and so the very labeling is not possible. But if you go by your intuitive energies, you will understand that this set has 0 elements inside it. This has just nothing, which means it has 0 elements. And therefore, we are able to list the members, which is nothing, with the help of not natural number, but a number which actually stops the process of labeling. And therefore, over here, in the case of empty set also, we have this declaration that yes, empty sets are also finite sets. So I'll write yes, phi is a finite set. This was a very nice observation. In my next lecture, I would be starting with a formal discussion about what finite sets actually are. Till then, you are advised to kindly work on these examples, think upon them, ponder upon them, and understand if there are any real life applications of these too, because I am sure you are going to be able to find tons of them. See you in the next lecture with much better spirits and energies and positive attitude. Till then, take care. Goodbye.